Okay, this slide, I'd like to introduce other way to identify the gain and also the problem statement that comes with the one of the frequently observed posture behavior. Okay, so for by observation, you can imagine that when you actually maintain a balance upright, there are different ways like you can maintain a balance by mostly using the anchor torque by make your body straight as a one single segment. And also you can also apply the torque at the hip and then bending your upper body forward and then maintain a balance, right? And then we observe that those ankle-centered sort of posture controls are usually observed for the response for the small perturbation or on a flat surface. Compared to that, those upper limb bending kind of posture control strategies been observed for the response to the large perturbation or on a balance on a narrow surface. Researchers also measure the muscle activity during those posture behavior. So for the left side, like an ankle-centered posture control, those EMG activation was activated from the farther side of the body toward the center, from the gastrocnemius first, and hamstring, and paraspinals. Okay, and for the hip joint bending kind of posture behavior is activating the joint muscle from the abdominal first and then quadricep. So there are two very different the control strategies observed in terms of kinematics wise, and the muscle physiology wise. So the researchers named it differently as this is ankle strategy and this one is a hip strategy, and then say that those very the distinct and different muscle activation patterns observed for the ankle and hip are stored in the beginning, and then depending on the perturbation profile, whatever the appropriate is been selected and performed. Again, anchor strategy is a sequential activation of the muscle from the distal to proximal, and then hip strategy from proximal to distal. To examine the transition from the ankle to the hip, well, actually, we actually had a similar sort of transition or whatever contributes more kind of approaches in walking. So for the passive walking, to compensate the collision loss, you have two options, right? Either hip joint torque during the single support phase or push-up energy provide during the double support phase. And then we did some work, impulse momentum change and work analysis to show that ankle push-up is mechanical work-wise more efficient than the hip swing actuation. So similarly here, so is ankle strategy is good for the small perturbation, often observed the small perturbation. Hip strategy often observed for the large perturbation. Why does that? Why does this different strategy observed as a function of perturbation? That could be one question to ask. And the other question is the transition from the ankle to hip is discrete or continuous? Okay, those are the questions we could ask. So we made a model for upper body and lower body, two segments. At least we needed two segments to demonstrate the hip strategy. And then since this is depending on the perturbation size, we designed the perturbation for the model as a backward perturbation for the surface. Okay, and then by varying the magnitude of the perturbation, we examine if the joint torque control or control gain varies. Okay. So if this is a linear control, you will have a constant gain, and then if you increase the perturbation magnitude, what will happen is your response will just uniformly scale. You wouldn't change from ankle to the hip or single segment to the two segment dominate responses, right? So what that means is your gain would change, okay? And maybe there are gain that will more representing ankle strategy behavior, and there should be a gain representing more likely hip strategy behavior. And then also as a function of perturbation magnitude, if there is a discrete switch transition from the ankle to the hip, there should be some region that ankle dominant gains are governed as a function of perturbation. And for larger perturbation, maybe there are discrete switch from the ankle to the hip. If those transition occurs in a continuous manner, like for the small perforation, there are ankle dominant, for very large hip dominant, but in between there might be some combinations of ankle and the hip strategy, then the feedback gain may look like more continuous changes. That's the hypothesis. So without further detailed explanations about what causes those gain scaling, I'm going to briefly just mention the hypothesis used in this study is like, since your applicable ankle joint torque is limited, so this means not your muscle limit, but your biological limit. Like when you're standing upright, you can apply the ankle joint torque, which is going to be proportional to your center of pressure location. So since your foot length has been limited, your maximum ankle joint torque is determined, assuming that your feet flat on the ground, right? So those ankle joint has a limit. You should actually switch the control strategy from ankle dominant control to the hip dominant. Okay, that was the hypothesis, and those transitions will occur in a continuous manner. So by running experiment, we measure the joint angle, and then using the joint angle, you can calculate the joint torques using the inverse dynamics, okay? And then since we know that those joint torque will be expressed by the feedback gain, Kx or K theta and theta dot, we identify the gain K. Instead of having regression K, which I just introduced from the previous slide, we do forward simulation. What that means is we just guess the gain K and just run the simulation and examine like this. I think the black one is experiment and the blue one is a simulation. Your forward simulation could demonstrate the data well, and then just examine, just do the trial and error by choosing the different gains. Like suppose you have a gain at like 1,000 is too stiff. So too stiff means like there are very, very small angular deviation. So you should you should tune the gain, like make it smaller. But if you choose wrong, then your system will divert. So at certain point, you will be able to, if you're lucky, be able to find some gain set that will well demonstrate the data. Okay, so that's what we assume as a feedback control gain K identified for that posture control motion. So by analyzing all the collected data using those gain identification method by forward dynamic simulation, we could examine what are the gain behavior or gain trends over as a function of perturbation. So the overall gain norm has been shown continuous decrease as a function of perturbation. This is observed for the healthy elderly. And that trend also observed for the young subjects as well. So we could tell that human posture control, the joint torques are well demonstrated by state feedback, like a joint kinematics feedback, and those gain K changes as a function of perturbation due to the constraint that you have a limited foot length. Okay. And for the patients who had a problem maintaining a balance, like a Parkinson's patient shows very, very stiff posture control, and they cannot scale their posture gain over the perturbation. That's the observation. So what that means is those posture gain control function has something to do with, maybe related with the part that the Parkinson's disease has a deficit in with. Okay, so far I introduced the way that we could identify the feedback gain K using the regression as well as dynamic forward simulation. And by describing the human posture with the feedback gain, we could explain some observed posture control behavior, like a smooth change from ankle strategy to the hip strategy as a function of perturbation.